For this project, our main topic focused on the fluctuation of house prices over a given time. The dataset that we used mainly allowed us to focus on the rent price and the sale price over the time period of around 1995 to 2024. This dataset served as the foundation of our analysis, and through this data, we were able to gather information and visualize it in the form of scatter graphs, bar charts, k-means cluster analysis, and etc. We also created a linear regression model that aimed to predict future house prices. Due to the apparent difference in house prices over the given time, we assumed that there would be further fluctuation in house prices in the future. So a linear regression model was created to predict the future changes.
So the data set that we chose was London property data, and this just showcases a comprehensive snapshot of London property sold between 1995 and 2024. So as you can see from the figure over here, it contains a mixture of both fixed attributes such as the location and the number of bedrooms, but also dynamic data such as the sales and rental estimates, and also the historical price changes. So the inclusion of the historical and current market data is useful for trend market analysis. And then we also have property specific data, which would be useful for real estate analysis, such as predicting the property appreciation or depreciation, also trend forecasting and investment modeling.
Here shows the summary statistics for the information in the dataset. We mainly focused on the mean, median, and mode values of our analysis. From this data, we can gain a general picture of the average London home. It tends to feature 1 bedroom, 1 bathroom, and around 93.97 square meters of area on average. When looking at the price points and comparing the mean to the median, however, we can see quite a difference in the price. One factor that may contribute to the skewed data that we are receiving from the mean could be geographical location. This is also supported by previous analysis done, where we saw that certain postcodes were more prone to a faster climb in sale and rent price than other postcodes. Looking at both the mean and the median for the current sale price and the historical sale price, both the mean for the current and historical sale price are quite skewed from their medians. This shows that geographical location could be a factor that affected both sale prices across the entire time span.
So we carried out exploratory data analysis prior to implementing our machine learning model, and this just allowed us to visualize and understand the patterns in our data. So the first hypothesis that we investigated was larger properties have a higher sales and rental price, and the rationale behind this is larger homes typically have a higher purchase price, which would equate to a higher rental rate. So here we have a scatter plot of the property size against the sales price, and as you can see, as the property size increases, the sales price tends to increase as well. We also plotted this for the rent estimate, and similarly we have, as the property size increases, the estimated rent price also increases. So the second hypothesis that we investigated was properties with a higher energy efficiency ratings have a higher sales price. And the rationale behind this is with a higher energy efficiency ratings, this will lower the utility cost, making the house more attractive to renters. So we created a heat map to visualize this. So we have the energy efficiency ratings on the x-axis, the property count on the y-axis, and also within the cells, and then a heat map showing the average sale price for each band. So there doesn't appear to be an observable correlation. We can see that Class B has the cheapest average price, and Class F has the most expensive average price, which would suggest this hypothesis is not supported.
To explore this dataset further, we decided to include a third hypothesis. We predicted that properties with more bedrooms and bathrooms would be priced higher for sale and for rent. In order to investigate this, we decided to use a correlation heat map as our visualization technique. This is because correlation heat maps are a very robust way of investigating simple relationships. They're also very visually intuitive, which means that relationships are presented clearly with this method and are very easy to understand. We ultimately found that there was indeed a positive correlation between the number of bedrooms and bathrooms with the rental yield and the sale price. I think it's also important to note that there was a slightly stronger positive correlation with the number of bathrooms and the rent and sale price.
The fourth hypothesis that we explored is that areas with lower sale prices have higher rental yields. The rationale behind this is that affordable properties can offer proportionally higher rental returns. This is because the demand for lower priced properties is inelastic, so they can charge proportionally higher rent prices, whereas higher priced properties are generally more elastic in demand. To test this, we plotted a scatter graph with the sale price along the x-axis and the average rental yield percentage by area on the y-axis. We found a negative correlation, which supports the hypothesis that areas and properties with lower sale prices have higher rental yields. The fifth hypothesis we aim to explore is whether properties with more bedrooms have lower rental yields in suburban areas compared to city centres. The rationale behind this is that families in suburban areas are more concerned about increasing the sale value of the house compared to the rental value, which will result in a lower rental yield. This may be because there are a larger proportion of homeowner investors who are looking to rent their properties in city centres compared to homeowners in suburban areas. To test this hypothesis, we plotted a bar chart with the number of bedrooms on the x-axis for both city centres and suburban area properties, and the rental yield was on the y-axis to be able to compare the two. We found that there was not enough evidence to support this hypothesis. The first machine learning algorithm used in this report was a linear regression model, and it was used to analyze the relationship between the outcome variable, which is the sale estimate of any given property, and multiple explanatory variables that include the number of bedrooms, the number of bathrooms, and the current monthly renting estimate. The model aims to predict the value of any given house in London. It estimates the weighted impact of each explanatory variable to evaluate how strongly each explanatory variable affects the outcome variable. Feature selection is a critical step in this process, as it considers the variance bias trade-off. The number of features selected in the regression was limited to reduce the risk of overfitting the model. The features that were selected are also highly correlated with the outcome variable to improve the accuracy of the model. The model is evaluated using metrics like the mean squared estimate and the R-squared value to test the accuracy and feature relevance. The data is also split into training sets and test sets with an 80-20 split to evaluate the generalization of the data. The second machine learning model used in the report was k-means clustering, and it was applied to group properties with similar characteristics together. Feature selection was also important in this model to reduce dimensionality. The features selected were the property size and the number of bedrooms. The elbow method was then implemented to find the optimal number of clusters. A scatter plot of the clusters was then produced with the property size on the x-axis and the number of bedrooms on the y-axis. The outputs of the regression are given on the right-hand side, with the weights of each explanatory variable being displayed. The results show that on average, having an extra bedroom increases the value of the property by around 17,500, and having an extra bathroom increases the value by 37,000, and an extra unit increase in the monthly rent is associated with an increase in the property value by £253. The R-squared value of the linear regression on the training set is 0.964, which shows that the model prediction fits extremely well with the actual data points. Therefore, the model has great feature relevance. The R-squared value of the test set is 0.966, which is almost identical to the training set, thus showing that there is minimal overfitting in the model. Overall, the linear regression model is very useful in predicting the value of any given house in London. It provides a strong basis for house price analysis, and it is robust enough to allow for new data to be added. The outputs of the K-mean clustering analysis is displayed on the right-hand side. Using the elbow method, the model successfully segmented properties into distinct groups based on their size and the number of bedrooms. There were 3 clusters produced, and they are smaller properties, and they typically have a floor area of below 80 square meters and 1 or 2 bedrooms. Medium properties show a wider range of floor area, generally accommodating 2 or 3 bedrooms, and larger properties have significantly larger floor areas and are likely to include 4 or more bedrooms. Overall, the model is useful when grouping properties with similar characteristics together.
There were many key takeaways we got from analysing this dataset. We discovered several factors and relationships which impact the London housing market. For example, we found that larger sized homes incurred higher sale prices. This was also true with the number of bedrooms and bathrooms, which also generated higher sale prices and higher rental yields. As mentioned prior, the relationship between rental yields and sale prices was also interesting to uncover, as we found that homes that generated higher rent were usually cheaper than the homes that generated lower rent and were more expensive. This gave us insights into the market trends in London, and it highlights that this data can be useful to tenants, prospective homeowners, and professionals in real estate. They can use this data to market properties towards tenants who are most likely to buy them for their aspects and their prices, and it will also help them to get to know their customers even more. As for tenants and homeowners, they are able to weigh out which aspects will be more beneficial to them while taking price into account as well. Another key takeaway that we got from this dataset is that there is a high disparity in London properties and affordability. In our statistical analysis, we found that the mean sale price was significantly higher than the median price, which indicated the presence of high value outliers in our dataset. It would have been beneficial to investigate this further and see where exactly these outliers were coming from, and if these higher priced properties were situated in certain geographical locations in London. This will help to highlight the imbalance of affordability based on area in the city. Lastly, our machine learning models were shown to be accurate when predicting the price based on size and number of bedrooms. We also used the K-means clustering technique, which was an example of unsupervised learning, to group our properties into different categories based on size. While this can be viewed positively, it can also be argued that there is a lack of applicability. Size is just one component that could impact house prices. There are several other factors such as distance to public transport, accessibility, and school ratings that can have an impact on price also. It is important to note that a truly representative model will include such aspects as well.
Overall, the analysis of this dataset allowed us to gain insights into the validity of our previous hypotheses and which ones should be carried forward when developing new technological models and which ones do not correlate to any rise in house price. Some examples of these predictions include larger floor area, more bedrooms, more bathrooms, and certain postcodes contributing to the increase in house price. These were backed by evidence from the analysis that was carried out, but some other experiments, such as energy efficiency, for example, did not seem to correlate to the difference in house price. As for the future development of our analysis, a linear regression model was created to predict the future house prices that may arise. This can be used by both the future buyers and the landlords, but some implications of this model included the fact that it only took into consideration quantitative data. But as seen by our analysis, there are quite a few contributing factors that concerned qualitative data, such as geographical location and different house prices depending on different postcodes. To be able to further develop this model, the model needs to be adapted to take into consideration all data types. This is to increase its accuracy and precision.